session and ask please to Professor Bruno Valette, who will chair the first talk, to start, please. Bruno, go ahead.
Thank you, Carlos. Maybe we should wait 1 or 2 minutes now because it's not 9:30. So maybe let me say one word about something that I know is the workshop that's going to take place in April and at the CRM. So let me first say that April 12th is going to be mid-spring, and I very much hope that by that time, COVID will be behind us, more or less. I mean that we'll be able to meet. So I hope that April is a good window, you know, to have the first in real life workshop. So as a consequence, I strongly encourage you to register for this kind of thing. There are going to be 5 lectures by 5 experts on higher structures and operatic calculus. And the idea is to provide you with a state of the art of what is going on in this domain. Today, you're going to have 2 beautiful talks by great experts, Ieke Moerdijk and Martin Markel, on this. So I hope that this talk will give you enough interest to join us in April. You'll have these 5 talks by young guys. And the idea is to address to everybody. So there are no prerequisites. We will not start from a very high level. So these 5 talks are going to be, I hope, great. So please join us, register, tell your colleagues, your students to register, and let's meet in Barcelona for the first time, say in April. Okay, now I think it's Ike's time to talk about varieties of trees. Ieke, are you with us?
I'm here.
Good. Are you ready?
Yes, but I have to share my screen.
We want to see you. So let me say before Ieke starts, okay, please turn all your microphones off during the talk so that we don't have any noise. If not, I will turn off your microphone. If I may ask your questions, I mean, we want this to be as living as possible. It's very frustrating to be behind a screen and not to be able to see you today. I hope Ieke is okay if you ask questions. And of course, we'll have a question and discussion session after Ike's talk. So if we all agree now, we can listen to Ieke.
I will start sharing.
Please.
So thank you very much for inviting me to give this first lecture. As has been emphasized by all of you who spoke at the introduction, it's we had all hoped to be in spring-like Barcelona. Instead, I'm sitting in my office in my home office in wintry circumstances. And as Emma emphasized, we are not escaping from our local duties, teaching and meetings and so on. So it's not the same type of conference as we had been hoping for, but we shall have to live with that. So I'm hoping to give a light introduction to various aspects of the theory of infinity operands. And I'm sure many things, much of what I'm going to say will be familiar to some of you. So I apologize for that. My main aim is to, in fact, to show the flexibility of the framework that I'm going to present. My talk is based on work with several collaborators, and I thought it would be good to mention their names right away. So they're on the bottom of the screen: Itai Weiss, Denisha Szynski, Gijs Heuts, Vladimir Hinic, who is here, Pedro Boavida, and Eric Hofbeck. There are certainly others who contributed to the theory: Javier Gutierrez, who is here, Basic and Nicolaus, Dimitri Ara, Moritz Goot, who worked with me, Geoffroy Aurel. Some of the names will appear later in the talk, but I just want to emphasize that this is a sort of a collective enterprise. The variety of trees that you see here, these are obviously an oak, a poplar, and a fir tree, but perhaps that's not so important. So now let's go to the next page. So there will be an, I'm sorry about the confusion. There will be an ambient a variety of trees. I say ambient because there will be many sub-varieties, which are called omega. And the thing to keep in mind is that this is a category of finite trees. They are rooted, and they may have stumps. Stumps are the little things here on top of a leaf. They need not have stumps. And what is important is that although I draw a picture, they're not planar trees. So if you look at the sheet from the other side, it will be the same tree. Okay, so a tree, I will introduce some terminology to be able to speak about these trees. So the tree has edges, and they come in three kinds. There is a root edge. There are inner edges, which connect two vertices, and there are leaves. So there are two kinds of outer edges, the leaves and the root. And the vertices are also divided into two classes, as it were. There are internal vertices, and there are external vertices. External vertices have an external edge attached to them. So the root is always an external vertex, and a stump is always an external vertex, and an external vertex which only leaves as incoming edges is another type of external vertex. Okay, and these trees form a category, and the morphisms are generated by 4 types of maps. There are isomorphisms, about which I will not say too much, but remember that they are there because the trees are not planar. And then there are two types of faces. External faces, where you can chop off an external vertex, so you can cut here, or you can cut here. The next page will give some examples. And there are inner faces, where you can contract an inner edge. And there are degeneracies, and a degeneracy will just put a unary vertex on an edge. Okay, it's important to remember the direction of these morphisms, so that will come on the next page. So here are some examples. So here's a tree. I label 2 vertices, this stump here and this root vertex here and this edge here. And then there is the face delta E. It goes from the tree which contracts the edge E back to the old tree. So if you contract E, this will become a composite vertex with 1, 2, 3, 4 incoming edges, those 4 here. And there are 2 external faces that I've drawn. You can cut off the vertex T, or you can chop off the root vertex. You can chop off the root vertex because there's a tree remaining. You cannot always do that. If it's because the root vertex has only one internal edge attached to it. In other words, the root vertex is an external vertex. It isn't always an external vertex. And here's a picture of a degeneracy. So I've put a new unary vertex on this edge, and the degeneracy collapses this edge. So this terminology extends the one for simplicial sets, and it also does so in a technical way, which will become apparent later. So we have the usual faces and degeneracies, and like for the category delta, there are external faces and internal faces. I drew another small example here. For this tree, you can chop off the vertex V you end up with this tree here. Or you can contract the edge E, this is example here. And if you now look at the intersection of these two maps, you will see that in the category you can map from this tree, which has no vertices, but it has the name D, that's the root edge here, or the edge C, that's this edge C here, but A, B, and E have disappeared. I've contracted A and I've chopped off I've contracted E and I've chopped off A and B. So I emphasize this example to illustrate that the intersection of two faces doesn't have to be connected in this setup. And in fact, that's the source of a lot of technical trouble, which I don't want to bother you with this early hour. To continue a little bit with the terminology, there are two types of special trees that I would like to emphasize. There's a unit tree, which we have already seen. It just consists of an edge, which is both the leaf and the root, and I call it eta. And there is a corolla tree with just one vertex and n incoming edges and leaves, n can be 0, so this is also a corolla. Okay, we'll see a few more pictures, I think, later on. Some more terminology, also to understand what goes on with these morphisms. So I've said that a tree has leaves, vertices, and edges. And for a tree T, I denote its set of leaves by lambda of T, and its set of vertices by V of T, and its set of edges by E of T. And now it's important to realize that a morphism from S to T I defined it now as being generated. It's a composition of these generating morphisms, these faces, degeneracies, and isomorphisms. There is a more global way of describing it on the second half of the page, but before you look at that, edges go to edges. So a morphism in the category from S to T induces a function from the set of edges of S to the set of edges of T. However, for the leaves and the vertices, it also does that, but in the opposite direction. So if you have a morphism from S to T, you find a function, partial function from the leaves of T to the leaves of S. So that's in fact a functor. So we have a functor from omega to gamma. Gamma is the opposite of the category of finite sets and partial maps, or finite pointed sets. That's the same thing. And it also induces a partial function from the vertices of T to the vertices of S, again in the opposite direction. And if you apply this point of view to the category delta, you obtain exactly the well-known duality between delta and its opposite, which can be viewed as linear orders and partial maps with convex domain, or linear orders with total maps, but then you have to give the orders endpoints. So let's go back to the pictures for a minute. So if you look at this map, for example, then on the it contracts the edge E, and the map on vertices sends these two vertices to this single vertex. Okay, it's a total map in this case. But if you chop off a vertex like this one, you have a map on the vertices in the opposite direction, and it will not be defined on the thing that you chop off. So it's again partial. Okay, if you want to see what it does on the leaves, so let's look at this tree here. You have to look at the image of the tree and trace the leaf down to the root and see where they hit the image. So, for example, the leaf here, A, will just be sent to A here, and it will be sent to E here. Okay. And if you have chopped off something on top, then this could result in a partial map. I'm not sure whether I illustrated that here. Okay, here's a more global way of defining the morphisms. So any tree T generates a colored operand. It's just an operand in sets. And the colors are the edges of T. And the operations are generated by the vertices of T. So let's again go back to the previous page. Let's take a simple example here. This is an operand with 1, 2, 3, 4, 5 colors. It has a binary operation from E, C to D, and a binary operation for A, B to E. And then it will have a composition, of course, from A, B, C to D, which is in fact illustrated exactly by this face. Okay. And it will also have symmetries. So if I draw a picture like this, there will be an operation from AB to E, but also it's twisting from BA to E. So these are symmetric operands. So another way to describe this category omega is just by those trees and morphisms, operand maps. So morphism can be defined in two ways: by generators and relations, phases and degeneracies, and so on, or as operand maps between the induced operands. These operands are free in some sense, right? Excuse me. So the this category omega has many interesting pre-sheaves on it. So contravariant functors to sets or to simplicial sets or to linear categories. And the first example that I would like to mention is that if you have an operand P, then the nerve, you can define the nerve, and that's a contravariant functor on omega, and is defined just as for the nerve of a category. The value of the nerve of P at a tree T will just be the set of operand maps from omega T to P. So it's in some sense a representable functor, but not represented within the category, but sort of in a larger category of operands. Now, there are not so many, well, there are many operands in sets, but usually operands have more structure. So I give another example here. If P is a topological operand, you can still define a pre-sheaf with values in sets. It's called the homotopy coherent nerve of P. And for various reasons, which may not become clear during this talk, I denote it by little w upper star of P. And little w upper star of P, its value at T is again a set of maps, but now it's homomorphisms from topological operands from an operand WT to P. So to the tree T, I can associate two operands. There's omega T, which is an operand in sets, and there's WT, which is a topological operand. And W of T is the Boltzmann-Vogt resolution of omega of T. Now, this Boltzmann-Vogt resolution of an operand is a complicated thing, but for operands of the type omega of T is very simple to describe. It's much like before, it's an operand where the colors are the edges of the tree, and the operations, they are again compositions of vertices, so they are like subtrees, but now I give the edges a length. And for now, I take this length in the unit interval between 0 and 1. So I do an example here for this tree. I look at operations from A, B, C to E. So A, B, C to the root E. And there will be a square of such operations. 2 cube because I can put a length here and here. Okay. The operations from U, V to B, it will just be a point because there is no inner edge between them that I can give a length. Okay. And for larger pictures of trees, if you compose such morphisms, you have to give the connecting edge, as it were, the edge along which you compose, have to give it length 1. Anyway, that's a very simple operator. You can think about it. All its morphism sets are cubes of a certain dimension. And you maybe one more word. Oh, it's written here. There's a map from W of t to omega of t, because you can just forget the lengths and then you're back into this world of 3 operators that I mentioned before. And this map is obviously some sort of weak equivalence because, as I said, all the morphism sets are cubes, so contractible. So that's why it's called a resolution. Here are some more examples. For the commutative operator, of course, its nerve is just a constant terminal presheaf. Its value is a point, a singleton at every tree. And for the associative operator, its nerve is the presheaf of planar structures. So if you give assign to a set its planar structures, that's in fact a presheaf. As the structure of a presheaf, and it can be identified with the nerve of the associative operator. So I made a small side remark here, to which we will get back in a minute. So you might be tempted to define the homology of an operator by just using this category omega. So you define the homology of a presheaf. I didn't write any coefficients, but take the coefficients to be z. Then for the nerve of COM, you just get the homology of the classifying space, B omega. And for the homology of the associative operator, you will get the homology of the category of the classifying space of the category of planar trees. But these categories are both contractible, so that's not a very good thing to do. And in fact, I will give a quick proof that to show you that these are contractible. Here's another example to which I will get back at the end of the talk, time permitting. And that's that if you have an algebra for an operator, you can also define a nerve, so if the algebra is A, I denote the nerve as nerve of P A, and it maps to the nerve of P. So if you look at the tree T, for example, small tree as pictured here, you can think of the nerve of P as labeling the edges by colors of the operator and the vertices by operations. So this vertex here is labeled by an operation P of the operator, little p of the operator, capital P, and it's an operation from B, E to A. Okay. Now, if for the nerve of the algebra, you will also have to label the edges by elements of the algebra. So I wrote them here X, Y, Z, U, and V. These are elements of the algebra, and they should come from the right colors of the operator. So this element Z is in A of C because this edge has color C. And there should be a compatibility with the labeling of the operations. So here you see the label Q, which is an operation from the operator. So Q of ZU should be Y. So in fact, if you label the leaves, you can recover all the other labelings just by applying these operations. So that's maybe a bit quick if you have never seen that, but just remember that you can also, there is some sort of nerve of an algebra which sits over the nerve of the operator. Okay. So this category omega shouldn't be viewed as carved out in stone, and in many contexts it is more convenient to use some variation of it. When's the title of the talk? And I'll just list a few here. Of course, you can look at just linear trees, and the usual way of denoting linear tree with n+1 edges is by brackets n. And in this way, the usual simplex category delta becomes a full subcategory of omega. And with this inclusion, a delta doesn't have any isomorphisms, but the faces and degeneracies keep their usual meaning. Then I write omega sub little o for the category of open trees. They have no stumps. Omega bar for the category of closed trees. They have no leaves. There is a category of reduced trees for which I didn't write a notation, and these are the trees without unary vertices. So for many, as will be obvious to many people working with operads, the nerve of an operad often lives really in trees which are both closed and reduced, because P of 1 is often just a point, just the identity, and P of 0 is also often just a point, just one constant. Or P of 0 can be empty, and then you're in the world of open trees, where you take its nerve. Okay, planar trees. And the main feature of the category of planar trees is that there are no isomorphisms left. And then I also mentioned two other aspects here. You can look at trees where you number the leaves. And you can ask morphisms to respect this numbering. And that's the same as looking at a comma category. It's usually done for open trees. So that's the same as looking at a comma category of open trees under the end corolla. So map from the end corolla to such a tree is the same as, this is a mistake, because then I should also preserve the root. Okay. Anyway, and there will also be a slightly smaller category where I exclude the corolla on this side. So I look at trees with at least one inner edge. I mention these categories because they're closely related, especially this one, closely related to partition complexes. So I think there will also be a remark about that. Oh, maybe it's here. Okay, so the category delta is just a slice category, omega over eta, omega over the unitary. So that's a special, the delta sits very canonically in omega. The category of open trees is also a slice of omega, but it's a slice over a large presheaf. The category of planar trees is also a slice of omega. It's the slice over the nerve of S. I essentially already said that. And here is something about the relation between arbitrary trees and closed trees. You can close off a tree by just putting a stump, a vertex, on top of every leaf. I denote it also as a closure. So, and that's in fact a functor. So I drew a picture here. So if you look at this constellation of trees, so this is a small tree, and I don't know what I did here. I pictured two morphisms, and these morphisms are both external faces. Now, if you close things off, you put bullets on each of the leaves, then of course this top face, so to speak, nothing happens. It's a top face here. Okay. But for this bottom face, which is this part here, which chops off this top leaf, you cannot chop off this leaf anymore. So this now becomes a composition of contractions. You contract this edge and this edge and this edge, and you end up with this tree. Okay. It's also maybe good to look at this morphism here, because you cannot chop off the root, because you don't end up with a tree, you end up with a forest, because this root vertex is not external anymore. There's an internal edge here. So you have to first contract this internal edge, then the root becomes unary and you can chop off the root. So this is in fact a composition of an internal face and the root face. Now here's a technical remark which I will not expand on, but is very important in developing the theory. In this category of closed trees, all faces are inner, except possibly the root. Okay, there are no external vertices on top that you can chop off, because if you chop off a stump, it will no longer be a closed tree, of course. So, and because of this problem of the intersection of faces being disconnected disappears, and that has lots of technical consequences when we look at homotopy theory and model structures. Okay, here's a little warning. You cannot do sort of an inverse operation and go from arbitrary trees or closed trees to open trees, because that's not going to be a functor. So there's no such thing as the interior of a tree being a tree. So just to repeat, these variations, closed trees are very convenient because all the faces are inner except the root. The simplices lie very nicely in this category of omega, and if you prefer to work with planar trees and non-symmetric operads, then in that case there's also a natural way of in which this is contained in the setup. Okay, so here's a little proof to illustrate that the classifying space of the category of closed trees is contractible. This will, of course, imply that the category omega, here it's written, B omega is also contractible, because we've just established the junction between omega and omega bar, between arbitrary trees and closed trees. And you can do the following, which you cannot do for arbitrary trees, but you can do for closed trees. You can define a functor which adds a root, a unary root at the bottom of a tree. I call it dec for décalage. And there will be natural transformations from the identity to dec, and from the constant functor, which has a value C0, to dec. And that will show that omega bar is contractible, because these natural transformations become homotopies, so the identity is homotopic to the constant functor. And here's a picture illustrating what's going on. So here's a tree T, it's a closed tree. Here is dec of T. I have this new vertex on the bottom. And here is the inclusion of this C0, copy of C0 as the bottom vertex. So this morphism contracts all the other edges, okay? And this morphism chops off this new root. Now, why is this functorial? So here's the sort of a non-trivial case to understand that. This map first contracts this edge and then chops off the unary root. So it's this top part, inclusion of the top part of the tree here. And if you add a bottom vertex to this tree, it's sort of at the wrong place. It's at this place here, okay? But there will still be a map like this, because you can first contract this edge and then have a degeneracy to contract this, well, and then it makes everything commute. I said degeneracy, I should not have said that. This is, in this case, you contract, first you contract this, the edge, and then you contract, which one will it be? This one. Okay. Okay, so here's so there's no contractable, no interesting homotopy type here because omega bar is contractible. Here I mentioned another example. If you look at open trees and you look at maps from the corolla which preserve the leaves and so open trees with N leaves and maps which preserve the leaves and the root, then the homotopy type of that space is a wedge of spheres. And if you want to see a nice proof of that, I mentioned the reference here by Sarah Whitehouse and Robinson in a paper of 1996. So that's there are of course many interesting things to do with trees, and this is one illustration. And this is in fact a very important example playing a central role in causal duality and representation of free Lie algebras. Okay. So another aspect of the theory is that there are tensor products. And the tensor product is defined as follows. If you take two trees, so maybe before I say something about this definition, this tensor product is meant to generalize the product of simplices. So there is a product of simplices, but if you take a product of two simplices, you don't get a simplex, you get a simplicial set. And that product of simplices is the union of several other simplices, okay? Delta 1 times delta 1 is a square, and is the union of two copies of delta 2, and so on. And so something similar happens here. And here's a global definition. If you have two trees S and T, that tensor product is not a tree, but it's a presheaf, and it's the nerve of the Boardman-Vogt tensor product of operads. So you form the Boardman-Vogt tensor product of these two operads, and then you take this nerve, and you get a presheaf on omega. And you can do that also for n copies, of course. You take the tensor product of the corresponding operad and then take the nerve. In that sense, it's better to think of this as an unbiased tensor product because it is not quite associative. This sort of interference with the nerve destroys the associativity. So, but there will be canonical maps like this. And I would like to emphasize that although these maps are not isomorphisms, they usually have very good properties. For example, if you work with open trees or with closed trees, they will always be anodyne. There will be trivial cofibrations in the model structures that we are going to consider. If one of the components is linear, so if you tensor a tree with a simplex, it's also always, these associativity maps always behave well. So although it's not associative from the point of the homotopy theory, it nearly is, and it behaves rather well. That last point about simplices is illustrated here. But before that, I mentioned another example. If you tensor with C0, that's the same as taking the closure. So let's look at tensoring with a simplex. T tensors a linear tree. So an arbitrary tree tensored with a linear tree is in fact a special case of the Cartesian product with something else. And that E of n is a presheaf, and its value on the tree R is very simply a labeling of the edges of R by the number 0 up to n. And the numbering has to go up as you go down along the tree. So it's just poset maps from the edges of R, where you order them from top to bottom, to the set 0 up to n as a linear order. Okay, so here's an example. Here's R, and here I number 0, 1, 2, 1, 1. So you see, if you go along a branch from a leaf to the root, the numbering goes up. So because of this, tensoring with simple initial sets has very good associativity properties, because essentially it just is a product. Okay, so this tensoring business can go can be extended to presheaves just by taking co-limits. So the category of presheaves on omega is called the category of dendroidal sets. The category of presheaves on delta is, of course, the category of simplicial sets. And this inclusion from delta to omega induces adjoint functors. So the simplicial sets are fully faithfully included in dendroidal sets, and every dendroidal set has an underlying simplicial set. Okay, and what I said in the beginning, when we started to talk about this tensor product, this tensor product on dendroidal sets extends the Cartesian product on simplicial sets. Now I also said that the Cartesian product of two simplices is a simplicial set, and that simplicial set is a union of simplices, and this union is indexed in a very precise way. It's indexed by the shuffles, and that plays an important role in many aspects of even the first steps in algebraic topology, Alexander Whitney maps and so on, Heilenberg-Zilber. And a similar description applies to tensor products. So the tensor product of two trees can be written as a union of shuffles of two trees. And I didn't write anything about this in the talk, but these shuffles are combinatorially extremely complicated, and we don't know how to count the shuffles. For example, it's easy to count the shuffles of a P simplex and a Q simplex. Is just P plus Q over P, many of them. And for two trees, it becomes extremely complicated. So you could look at whether there's more structure on this set of shuffles. Of course, even for simplices, they're ordered in a natural way, partially ordered. The same is true for shuffles of trees, but it doesn't seem to help to count. So if there is a combinatorial list in the room, you can say something about that. I would be grateful. Okay, so this part was meant as a first introduction to the category of omega and what you can do with it. And now there will be a bit of a jump, and I would like to survey some aspects of the homotopy theory of these dendroidal sets and dendroidal spaces. And I wrote several papers about this, notably with Szyczynski and with Heutz and Hinich, and with Pedro Barrovido, who I mentioned in the beginning. And I'm in the process of writing a book with Gijs Heutz, and you can also view what I'm going to say as some survey of some aspects of what is in this book. and large parts of the book are in fact available on either of our home pages. So you could, if you're interested, please do take a look there. And you will also see that, of course, I've been hiding all the technical complications because working with trees is quite a bit harder than working with simplices. So the dendroidal sets cause a lot of trouble compared to simplicial sets. And if I summarize it, the trouble or the combinatorial complication, I mean, it's said trouble, but the trouble can be solved, but or worked around. But the complication arises really from these two very elementary aspects that I already mentioned, namely the intersect. Unlike for simplices, the intersection of two faces doesn't have to be a face, and can be disconnected. That's one. And the other is this almost associativity, which you have to very carefully keep track of the tensor product. Okay. So there are all kinds of Quiller model structures on dendroidal sets, which extend the model structure on simplicial sets, or read in the reverse direction. If you have a Quiller model structure on dendroidal sets, then you have a model structure on any slice of it. In particular, if you slice over eta, you obtain a model structure on simplicial sets. So the first one, historically, is what is called the operatic model structure on dendroidal sets, which originates with my paper with Szynski. So sometimes it's called the Szynski Moerdijk structure. And if you slice it over simplicial sets, you get the Joyal model structure on. If you slice it over eta, sorry, you get the Joyal model structure on simplicial sets. So it's some extension of the Joyal model structure. So here, the fibrant objects are called the infinity categories, or quasi categories, and the fibrant objects here are called infinity operads or quasi operads. And this model structure derives its importance from the fact that it is Quillen equivalent to the category of simplicial operads. So simplicial operads, by simplicial operads, I mean symmetric operads, which are colored. Okay, so I allow multiple colors in the operad. I don't have to, of course, but there's also a variant of this where the operads only have one color. But in general, it works in this generality. Okay, now if you go down, you can keep the cofibrations the same, but increase the weak equivalences. So that's the method of left Bousfield localization. And the first step down is the covariant model structure on dendroidal sets. And if you do this localization and then you slice over eta, you immediately tumble on the classical Kant-Quillen model structure on simplicial sets. There's no such thing as a covariant model structure on simplicial sets. Absolute. Okay, and this model category is Quillen equivalent to the category of Barrett-Eccles algebras. Okay, algebras for the Barrett-Eccles operad. More generally, you can do a covariant model structure on dendroidal sets over this homotopy coherent nerve of an operad that I talked about before. And then this is a model, this is a combinatorial model for the category of P algebras. So P is a simplicial operad. You can take P algebras in simplicial sets, or you can do it topologically if you prefer. And this is some sort of combinatorial model for it. There will be Quillen equivalence from here to there. There are various ways of viewing this Quillen equivalence, and I will say something about it towards the end of the talk. If you slice over eta, so in this middle column, then you lose a lot of the homotopy coherent nerve of P, and if I'm not mistaken, what you get is you just remember the unary operations of the operand. In other words, there will be a simplicial category inside this simplicial operand, and you take its homotopy coherent nerve, and then you obtain the covariant model structure here. And there's the well-known procedure of rectification or strictification, which makes this equivalent to simplicial presheaves on this category. So that's sort of a special case of the outer equivalence between covariant model structure here and P algebras here. Okay, so here are some remarks about these model structures. So the first remark I already mentioned, going down in a column is just a matter of left bow split localization. So the cofibrations are the same in all the cases. And in fact, the cofibrations are very simple to describe. And they also illustrate the difference between simplicial sets and working with trees, because trees have automorphisms. So a map from X to Y is a cofibration if for any tree T, if you look at the values at T, you have X of T, which you can view as a subset of Y of T. It's a monomorphism. And the automorphisms have to act freely on the complement. So this type of condition, of course, will be familiar with to people who work with simplicial sets with an action of a finite group, for example. There will be a similar model structure with a similar description of the cofibrations. Okay, and let me also mention the last localization in the column. So that's a model structure which was introduced by Matija Basic and Thomas Nicolaus, and they called it the stable model structure. We prefer to call it the Picard model structure for various reasons. First of all, it's closely related to Picard categories, but also it's not quite a stable model structure in another sense. So this terminology of stable, although I understand where it comes from, could be slightly misleading. This localization of dendroidal sets also corresponds to the Kant-Quillen model structure on simplicial sets, classical one. And now it's Quillen equivalent, as they proved, to connective spectra. So that's group-like Barrett-Eccles algebras. So from here to there, there's a group-like condition. Okay, so let's look a little bit more closely at the fibrant objects in these model structures. So I told you the fibrant objects here are called infinity operands. And they are defined by a right lifting property with respect to inner horns. So inner horns exactly as for the Joyelle model structure. But you have to think a bit more closely about what an inner horn could be. So that's on the next page. So these inner horns are denoted as for simplicial sets by a lambda. So there's lambda and a superscript E of T. It will be a subobject of T, and I view this for any inner edge of T. So it's the union of all the faces of T which contain this edge E. So you can obtain a face by chopping off part of the tree or by contracting edges, but you should never contract the edge E, and you should never chop off so much that E disappears. So here's a very simple example, sort of the minimal example. Here's the inner edge E, and there are three faces. You can chop off the top vertex, you obtain this face. You can chop off the root vertex, you get this face. They both contain the edge E. Or you can contract E, that's the third face, but that third face is a part of the boundary of the tree T, but is not part of the inner horn. Okay? And so the right lifting property with respect to these guys define define infinity operands, just as they define infinity categories in the Joyal model structure when the trees are linear. Okay, I talked about these two localizations going down in the left-hand column, and they're very simple to describe. For the covariant model structure, if you take a tree T, then any leaf of it defines a map from eta to T. You just chop off everything else until you're left with this tree, with this eta. And if you do that for all the leaves, you get a map like this, okay? And you force this map to be weak equivalence. You left Basfield localized for these maps, and then you obtain the covariant model structure. Now, for the stable or Picard model structure, you have to do one more thing, which will also look familiar to many of you. If you look at this binary operation, as it were, from BC to A, so think of that as a tensor product, B tensor C to A, is equal to A. You want to have an inverse for A, so you invert the inclusion of A and B. So the inclusion of B and C to A has already been inverted by this procedure, and I also make it group-like. Okay, so this is, as it were, I recover C as A times B inverse. The idea. Okay. Now, this all sounds very simple, but if you want to work with these, then you need to know a lot more about these lifting properties. So, for example, what Basis and Nicolaas did was to prove that if you have this localization and the leaf localization, you in fact, that's equivalent to asking the right lifting property with respect to all the horns. So they call it fully count. So not just inner horns, but an arbitrary horn will be the union of all the faces except one. So you're also allowed to take the union of all the faces except a given outer face. Could be the root face or a top face. And similarly, the localization for the leaves is in fact equivalent to the right lifting property with respect to all the inner faces and all the inner horns, sorry, and all the horns defined as the union of all the faces except a given top face, where you chop off a vertex. So we call that a top horn or a leaf horn. Okay, I mentioned these, let's go back one page. I mentioned this Quillen equivalence between the operatic model structure and simplicial operats. And there are variations. If you want to work with, there's something similar for open trees, and you just get simplicial operats without constants. And the category delta against it nicely sits inside it. And that's a very easy consequence because open trees, in some sense, form a slice. I think I already said that of omega. For closed trees, the situation is a bit more complicated, but there is a Quillen equivalence between a model structure, similar model structure, on closed androidal sets, pre-sheaves on omega bar, and what are called unital simplicial operats. So unital operats are the operats where, for those of you who work with operats with just one color, or P0 is a point, and for colored operats you have to say that P for any color C, the set of nullary operations with output of color C is just a point. So for every color, there's a unique constant. Okay. So now we take a slightly different perspective. I observe that all these categories of trees are reedy categories. And because of this, if you take pre-sheaves with values in simplicial sets, it has a nice, very standard model structure. So any functor category will have a projective model structure. And in this case, there will also be a reedy model structure. And in many cases, it's more convenient here to work with the reedy model structure. And now there is a similar sequence of model structures. And if you localize the reedy model structure for graftings, so if you have a grafted tree, T on top of S, then both S and T sit inside it. And if you localize for this, you get the fibrant model structure, the fibrant objects of which are called dendroidal Siegel spaces. And then if you also localize for one of the endpoints into the nerve of the single isomorphism, this gives you complete Siegel spaces. And this model structure will again be equivalent to the one on dendroidal sets. And I didn't write a column for the slice over eta here. Maybe it occurs on the next page, but if you slice over eta, this will exactly give you the complete Siegel spaces of Charles Resk, which are simplicial spaces. Okay, and you can, I will go a little bit faster. You can do something similar for the covariant structure. So work with dendroidal spaces and localize for the maps like we did before. And it will be equivalent to the dendroidal set case. You can do something similar for the operats. There's one important difference though here. If you work with pre-sheaves with values in simplicial sets, it's no longer necessary to take the homotopy coherent nerve. You can just take the naive simple nerve. The nerve of an operand in sets is a pre-sheaf with values in sets, as I mentioned at the very beginning. And if you have a simplicial operand, you will get a pre-sheaf with values in simplicial sets. And there will also be a Picard version of this. Okay, there are what's also technically extremely handy is that if you work with simplicial pre-sheaves, this business about closed or reduced was no unary vertices, I remind you, can just be done by left bias with localization again. So if, for example, let's look at this example here in the middle of the page. If you localize for this map from eta to C0, then it becomes Quillen equivalent to simplicial pre-sheaves on omega bar with a suitable model structure. So that's technically handy. A localization, a left bias fit localization on one hand becomes equivalent to shrinking the index category omega on the other. Okay, I'm going to skip the. I want to move towards the end, so I'm going to skip the rest of this page. Okay, maybe this is a final example, and it's based on my work with Pedro Boavida. So I already mentioned there's always a projective model structure, and sometimes you have to work with a projective model structure. And here's the example. If you consider the functor from omega to gamma, which assigns to a tree its set of leaves, remember this is just this is a functor from trees to partial maps and partially defined maps, and it's contravariant, but that's exactly the category gamma of Graham-Siegel. So any such functor will always induce a equivalent pair between the associated projective model structures. Now, if you take the projective model structure on dendroidal spaces, simplicial presheaves on omega, and you localize for the covariant model structure, so that's the insertion of the leaves, exactly as we did before, you naturally end up in gamma spaces with what is called a special model structure. So the special model structure, the fibrate objects, if you don't remember, the special model structure, the fibrate objects in the special model structure are the axes for which x of a plus b is x of a times x of b, where a and b are finite sets. And what we prove is that this is a equivalent equivalence. Okay, and of course, if you move from the projective model structure to the real model structure, this will be equivalent equivalence. And if you localize on both sides for covariant, it will remain a weak equivalence. And this you can model with dendroidal sets. So in this sense, you will move from dendroidal sets to Barrett-Eccles operats, or if you localize one step further for the group-like business, you will obtain equivalent equivalence. So I will pronounce this slowly, from the stable model structural dendroidal sets, the Barsic-Nicolas structure, to the dendroidal spaces with the group-like localization of this model structure, to gamma spaces with what is called a very special model structure. I think I mentioned Barsfield-Friedlander on the next page, which is a good reference for these model structures on gamma spaces. And that's a standard model for connective spectra. There's also a way to go more directly from dendroidal sets to gamma spaces, which was studied by Gijs Heuts, but it's maybe not necessarily simpler. So maybe this is the last page. So here are a couple of aspects about the proof, which are interesting by themselves. Let's look at the second thing first. What you need to show is that if you look at dendroidal space over the nerve of P with a covariant model structure, so this is a model category which is equivalent to the category of P algebras. It's some combinatorial model for P algebras. In this category, if you take the free P algebra on a single generator and you take its nerve, remember that you can also take the nerve of algebras, then it becomes equivalent to just this generator. So the insertion of the generator becomes a trivial cofibration in this model structure. Okay, so that's one aspect. And this statement here is something of, if you look at it in the right way, it is something of the same nature. You can look at the category sigma of finite sets and bijections. That's a symmetric monoidal category. And like for any symmetric monoidal category, there's a gamma space associated to it. And that gamma space has inside it a point. This is the representable on the point. So a point is just the identity on the one-point set that sits inside the finite sets and bijections. And it's sort of a basic ingredient of the fact that gamma spaces with a very special model structure, model connective spectra, that this is a trivial cofibration in the Barsfield-Friedlander model structure. But what we had to do was to improve this a little bit and get rid of this very in the very special. The very is the group-like localization, and we needed it for the special localization. So here's just special. Okay, so in fact, this map is a trivial cofibration in the special model structure. And the way Pedro and I proved this was by making very good use of, by playing the projective model structure and the reading model structure on gamma spaces against each other. So that's was somewhat technical, but okay. This is indeed the last page. So I would like to thank you for your attention. I would like to emphasize that there's of course much more to say. I didn't talk much about technicalities or proofs or more concrete examples. I didn't talk, I would have liked to expand perhaps a bit more on this issue of homology and what to do about this because of the contractibility of omega. But we have an entire semester to discuss this, so I'm sure there will be another occasion. So thank you for your attention and for offering me the occasion to speak about these things.
Thank you very much. Before the rest of the program, we may take 5-10 minutes to ask questions for more details or more examples. So I see you are something like 100 to be connected. Feel free to ask Ieke some questions. Go ahead. So don't be shy. If you have any question, turn your camera on, your microphone on, it's helpful. And then ask.
Maybe to break the ice, there was a question asked through the chat several minutes ago.
Okay, I didn't check.
Whether the definition of tensor product actually applies to arbitrary pre-sheaves. Of course, I assume it's yes, but how it goes? Maybe Ieke can say something about that.
Yes, so the way to do that is, I think it's on the next page, but it's very much like for simplicial sets. So let me first say how this works, which I'm sure known to everybody, but it's completely analogous. So you define for two simplicial sets delta m times delta m as a union of n plus m simplices. And then this in fact defines x times y because any simplicial set is a colimit of representables. So if you want the tensor product to preserve colimits in each variable separately, it's completely determined by what it does on the representables. And here it works in the same way. You define the tensor product of two representables as a pre-sheaf. And then if you have two arbitrary dendroidal sets, you write them as colimits of representables and you extend. So that's what it was very cryptic. I have to admit that, but it was just this sentence, now extend to pre-sheaves by colimit.
Thank you. So I understand that your book is already more than 500 pages, right? I've been checking.
Well, I think now it's still under, but I think it will be around 500, yeah.
Okay. I have one short question. You've been defining infinity opérade as a property, like for infinity category, you ask for the existence of Horn fillers. What about asking that it is a structure? This is something which appears when you do, for instance, higher Lie theory, when you integrate L-infinity algebras to create an infinity groupoid. Actually, the structure is algebraic. It's not only a property, but you have canonical Horn fillers. Does this phenomenon appears also for infinity operades?
No, I don't think there's anything canonical. You can, of course, define an equivalent model structure, or I say of course, but I suppose you can define an equivalent model structure by having fillers as structure maps. And I think Thomas Nicolaas wrote a paper about this, how to do this in general, but I don't know offhand how general his approach was, but his main example was simplicial sets and Kant complexes.
Yeah.
So there is a technical way of doing this, but I don't think it answers the question when you mention the word canonical.
No, but what his definition is now he has something which is an algebra over a monad if you ask for the structure. And what I'm saying is that such examples arise in nature. When you do integration theory of L-infinity algebras, you have this algebraic strong complexes anyway. I was wondering whether you have examples of this shape in the context of infinity opera.
Okay. No, I understand your question.
Yeah, sure. I know. Is there any other question? Feel free, don't be shy, please. Remember what Raoul Bott used to say. Raoul Bott used to say that there are no stupid questions. It's just stupid not to ask the question.
I have a counterexample. I have a stupid question.
There's no stupid.
No. Just a bit of intuition. I mean, so you said that when things have the lifting property with, I mean, some things have lifting property with respect to inner horns. Other things seem to have lifting property with respect to all horns. But then you mentioned something inner or top. Do you have any intuition about that?
I think that when
I mean, infinity groupoids and infinity categories are my intuition for the other two.
Sorry?
So for the other two cases, I mean, infinity categories or infinity groupoids are my intuition for two of the cases.
I think you're asking about this situation here.
I think it was.
So I'm not sure whether I understand your question, but what I said was that if something has the left, if you left localize for these maps, you force certain maps to be weak equivalences. Okay, you force these to be weak equivalences, trivial cofibrations. The trivial cofibrations are closed under 2 out of 3 among the cofibrations. And then if you just do this, then the inner horns will become a consequence, and also the horns which are called top horns, where you take the union of all the faces except one given by chopping off a top vertex. Yeah. And
yeah, I think I understand your definition. I don't know. I have no feeling for.
So that typically, yeah, maybe another thing I can say about it, when it comes to the intuition, when I spoke about the nerve of an algebra over an operad, I think the picture is still somewhere here. Okay, if you're giving a simplex in a nerve, and you want to lift that simplex to a simplex in simplex in the nerve of the operad, and you want to lift that to a simplex in the nerve of the algebra, it's enough to give the values on the leaves, because the value on the other edges has to come by applying the operations. And that's exactly saying it has the right lifting property with respect to these inclusions of leaves, this localizing map. So maybe that's the best illustration of the intuition behind this localization. Does that help?
I have to look at it. Yeah.
There is a question on the chat if you feel like you want to answer it. Is there an analogue of Thomson model structures for operad?
I don't know.
Good answer.
I know that people are thinking. Some people have been thinking about this, but I don't know the ultimate outcome.
Okay.
Is Matija Basic here? So he thought about this, for example.
Too many people.
He would speak when he was here.
Okay. Is there any other question?
Are you going to say anything about the little W star notation for the homotopical hidden nerve?
Yes. So when you let me also go to another page. So there is an equivalent equivalence between dendroidal sets and simplicial operads. And it is obtained by extending the capital W from omega to simplicial operads. So the Bourdon-Vogt resolution gives for any tree a simplicial operad, and that induces an adjoint pair of functors for which a common notation would be W upper star and W shriek. And that pair of adjoint functors gives you this equivalent equivalence from here to there.
Okay, thank you. That's it. Yeah.
Ima is a bit shy. She's asking the question in the chat. She said, why, which is unusual, why don't you like to call the model category stable and you call it Picard? Can you elaborate on that?
Well, there is such a thing as a stable model category. So if you have a equivalent model category, there are suspension and loop functors, and if they are mutually inverse, that's roughly speaking the definition of a stable model category. And this localization is not a stable model category in that sense. So it might be a little bit confusing.
Okay,
that's the only reason. No.
Sorry. So I propose to stop here. I think we deserve a break, because being online all the time is not that good. I propose to make a break here and resume in 8 minutes at 11 a.m. for Martin's talk. It's going to be closely related because he's going to talk about operas which have some tree-wise structures. Okay. I propose that we thank Ieke again for this great introduction to the program and to the conference. Thank you, Ieke, again.
Thank you.
See you soon.
Thank you, Ieke, so much.
Yeah, thank you. It was great. Yeah.
Well, I know we are out of time, but if you have any intuition for what is Haiger, Seagull, dendroidal, please let me know.
If I have some what?
Yes, for Haiger, Seagull, dendroidal. You have spoken a lot about dendroidal Seagull, right? But not, well, I understand you mean Guan Seagull, right?
You mean you want me to do infinity n operads?
No, I mean, I just asked if you had already some intuition, which may well be the case. But as you said, we have all the program. So
Yeah.
we can take a 5 minutes rest right now.
Yes, I would like to take a coffee before Martin starts.
I need to take some pills as well. Thanks again for your wonderful talk.
I will close the recording now. Huh?
Yeah.